Okay, so reactions go faster when there are a higher concentration of reactants. They go slower when there's a lower concentration of reactants. But how can we use these data, these findings, to build a case for the atomic theory of matter? I mean, for most of human history, it was just the atomic theory of matter was not a thing. It was not accepted. It was believed that there was no smallest thing in the universe. So how can we build a case for the atomic theory of matter from this experiment? Well, two scientists, Max Troutz and William Lewis, put some thought into this in the early 1900s. And what they envisioned was, if atoms are a thing, to react, they must be near each other. They must collide. Two atoms can't react if they're on opposite sides of a room. They actually have to come in contact with each other. So they just kind of started with this almost thought experiment, or this visualization. Like, if atoms do react, if atoms exist and they do react, they have to come in contact. Well, let's take a look at our experiment. So this is just a rudimentary model of our experiment. So here's the TUM tablet in the solution with a lower concentration of vinegar. Here's the TUM tablet in the solution with a higher concentration of vinegar. And these X's, of course, just represent acetic acid molecules. So here we have more acetic acid molecules. And you can see for the, or you can, just kind of visualize, for a reaction to occur at the TUMs, no reaction is going to occur until one of these molecules comes and makes contact. And at that point in time, there's a reaction. Carbon dioxide is produced, water is produced, calcium acetate is produced, but it doesn't occur until this molecule comes and strikes it. Well, if you have more molecules moving around, there's going to be more times, and there's going to be more events in a particular span of time where there's a reaction that's going to occur. So if I have twice as many molecules over here in any period of time, I'm going to have twice as many collisions, and each collision results in a little bit of this TUM getting reacted and therefore getting eaten away. So this was the simple picture that was used to defend this idea of atoms existing. And the last thing to touch on is this idea of reaction rate. I mean, what we calculated here was reaction rate. And think of reaction rate in a similar way to how you think about speed of a car, or speed of how fast somebody walks or runs. So speed is measured in distance over time, so miles per hour, meters per second. So it's per time, it's distance per time. So reaction rates are very similar, but you're not measuring the distance per time, you're measuring how much per time. And so reaction rates are usually expressed in grams per second. So I'll just write that down. So a reaction rate is usually spoken about in terms of mass per time, which, if we're using metric, that's grams per second. And so this is precisely what we were able to measure in this experiment. We had a loss of mass of each of these TUMs over a period of time. That mass loss, mass per time, is a way to represent reaction rate.